Rosalind Elsie Franklin was born on the 25th of July 1920 in London, England, into an influential Anglo-Jewish family. She was the second of 5 children in a household that valued intellectual pursuits, philanthropy, and education. Her father, Ellis Franklin, worked as a London merchant banker and served as a lecturer at the city's working men's college. Her mother, Muriel Whaley, came from a distinguished family with deep academic roots. The Franklin household was progressive, combining strong Jewish traditions with a liberal outlook on society. From an early age, Rosalind displayed a sharp intellect, strong determination, and a natural inclination toward problem-solving. Family members noted her tendency to ask probing questions about the world around her. She was particularly fascinated by how things worked, often dismantling and reassembling household objects to understand their mechanisms. Her curiosity was not limited to physical objects; she questioned natural processes as well. Friends and relatives later recalled that she exhibited a relentless seriousness, even in childhood, preferring intellectual challenges over casual play or idle amusement. Rosalind attended St. Paul's Girls' School in Hammersmith, one of the few institutions at the time that encouraged girls to study advanced science and mathematics. The school's environment fostered her scientific passion, with teachers who emphasized rigorous thinking and critical inquiry. She excelled in physics and chemistry, subjects often discouraged for women in that era. At St. Paul's, Rosalind began to distinguish herself as a student destined for academic excellence. Her teachers recognized not only her intellectual capability but also her perseverance, which often exceeded that of her peers. Despite being part of an affluent and supportive family, Rosalind faced cultural expectations that women should prioritize marriage and domestic responsibilities over professional careers. However, her parents encouraged her educational ambitions. Her father, though initially hesitant about Rosalind pursuing science, eventually supported her aspirations. Her mother consistently defended her independence. This balance of familial support and her own unwavering determination positioned Rosalind to overcome societal barriers. By the time she finished secondary school, she had developed a clear goal: to pursue higher studies in chemistry. In 1938, Rosalind enrolled at Newnham College, Cambridge, one of the few institutions offering women opportunities in the sciences. Cambridge at the time was steeped in traditions that often excluded women from full academic participation. Nevertheless, Franklin immersed herself in her studies with remarkable focus. She specialized in chemistry, a field she believed offered the best pathway to meaningful research. This choice reflected both her scientific strengths and her desire to contribute to practical applications. Despite obstacles, Franklin thrived, quickly gaining respect among her peers and professors. At Cambridge, Rosalind encountered both opportunities and challenges. Women students were technically not granted full degrees until 1948, which meant she initially studied without the promise of equal recognition. Yet, she pressed forward, immersing herself in rigorous coursework and laboratory practice. Her peers often described her as intensely serious, prioritizing her research above social engagements. This dedication occasionally isolated her, but it strengthened her reputation as a highly competent scientist. Her early work in physical chemistry at Cambridge set the foundation for her later groundbreaking contributions. During her time at Cambridge, Rosalind also cultivated an interest in experimental methods. Unlike many theoretical chemists of her generation, she was drawn toward the precision of laboratory work. She enjoyed manipulating equipment, designing careful experiments, and analyzing results meticulously. This emphasis on hands-on science would later define her career in crystallography. She believed that only through rigorous experimentation could theories be validated. This mindset shaped her approach to research, which emphasized empirical evidence, reproducibility, and clarity. Such traits eventually led her to scientific breakthroughs, particularly concerning DNA. Franklin's undergraduate years coincided with the growing influence of quantum mechanics and molecular science, fields that were reshaping chemistry. While much of Cambridge's curriculum was rooted in classical approaches, she absorbed new scientific developments with enthusiasm. She demonstrated a particular affinity for crystallography and X-ray diffraction, techniques that would later become central to her career. At the same time, she grappled with the cultural and institutional sexism of her environment. Despite this, her academic excellence was undeniable. She graduated with distinction, marking the beginning of her professional journey. In 1941, Franklin graduated from Cambridge with second-class honors in her final exams, technically making her eligible only for an ordinary degree. However, in recognition of her outstanding research skills, she was awarded a research scholarship. This scholarship allowed her to continue working at Cambridge under Ronald George Wreyford Norrish, a Nobel Prize-winning chemist. Unfortunately, Franklin and Norrish did not have a productive working relationship. He was known to be difficult, often dismissive of women in science. This strained dynamic eventually influenced Franklin's decision to pursue opportunities elsewhere. Frustrated by the limitations at Cambridge and eager to make a meaningful contribution during World War II, Rosalind shifted her focus toward applied science. In 1942, she accepted a position at the British Coal Utilisation Research Association, BCURA. This decision marked a pivotal turn in her career. At BCURA, she studied the porosity of coal and the behavior of carbon under heat, research that had direct wartime applications. Her work was critical for improving gas masks, fuel efficiency, and the development of new industrial processes, contributing significantly to Britain's war effort. At the British Coal Utilisation Research Association, BCURA, Franklin investigated the microstructure of coal, particularly its porosity and capacity to absorb gases. This research had immediate relevance during World War II, as coal was essential for energy and defense industries. Her studies provided crucial insights into the efficiency of coal as a fuel, enabling better design of gas masks to protect soldiers and civilians. Her contributions were widely acknowledged as valuable, and this experience further sharpened her ability to combine theory with practical scientific application. While at BCURA, Franklin worked with a team that emphasized problem-solving under wartime urgency. The environment required precision, quick thinking, and adaptability. She developed expertise in experimental techniques, including microanalysis, which demanded great patience. These years were formative, solidifying her reputation as a meticulous and hard-working scientist. Despite the practical focus, Franklin's intellectual curiosity remained broad. She saw coal research as both a professional duty during war and a stepping stone toward more advanced scientific investigations. This period also demonstrated her resilience in a male-dominated professional world. By 1945, Franklin had earned her Ph.D. from Cambridge for her work on the physical chemistry of solid organic colloids, with a focus on coal. Her doctoral thesis demonstrated originality, precision, and a capacity to translate laboratory research into meaningful industrial applications. Obtaining her Ph.D. was a significant achievement, particularly as women were still fighting for recognition in academic science. With this credential, she sought broader scientific challenges. The war had ended, and Rosalind was ready to expand beyond applied research to explore more fundamental questions in chemistry. After completing her doctorate, Franklin accepted a position at the Laboratoire Central des Services Chimiques de l'État in Paris in 1947. This move proved transformative. In Paris, she worked under Jacques Mering, an expert in X-ray crystallography. Mering became an important mentor, teaching Franklin how to apply X-ray diffraction techniques to study the structure of carbon and other complex materials. These methods required extraordinary precision, patience, and interpretive skill, qualities Franklin already possessed. The Paris years became a turning point, enabling her to master crystallography, the tool that later defined her legacy. Paris offered Rosalind more than just professional growth. She found in Mering's laboratory an atmosphere of collaboration and mutual respect, in contrast to the dismissive attitudes she had often faced in England. The French scientific community welcomed her contributions, and she thrived in the intellectual environment. She also embraced Parisian culture, enjoying the arts, friendships, and independence that the city provided. Friends later recalled her as more relaxed during these years, balancing her serious scientific work with a richer social life than she had known before. In Paris, Franklin made significant contributions to the study of amorphous solids, particularly carbons and coals. She developed a new classification system based on their microstructures, providing clarity in a field previously marked by confusion. Her research led to several important publications that established her as an authority in this area. The ability to classify and understand materials at the molecular level was an essential step for industries ranging from metallurgy to fuel technology. This work, though less famous than her DNA research, represented a major scientific contribution. Franklin's growing expertise in X-ray crystallography placed her at the cutting edge of post-war science. The method allowed researchers to examine the arrangement of atoms within crystalline and semi-crystalline materials. At a time when structural biology was beginning to emerge, these techniques were revolutionary. Franklin's careful, systematic approach enabled her to extract meaningful patterns from complex diffraction images. The skills she honed in Paris became the very ones that later allowed her to produce the crucial DNA images that reshaped biology. Paris thus prepared her for history's defining moment. While thriving in Paris, Franklin also remained closely connected with her family in London, particularly her younger sister, Jennifer, with whom she exchanged letters. These letters revealed her deep love of science, her occasional frustrations, and her growing confidence as a researcher. They also displayed her wit, sharp observations, and sometimes critical assessments of colleagues. The letters became an important record of her personality, disciplined, perceptive, and principled. They also highlighted her struggle to balance personal relationships with the all-consuming demands of her scientific career. By 1950, Franklin had established herself as an expert crystallographer, but she began to consider returning to England. Despite her love of Paris, opportunities for long-term advancement were limited. Moreover, her family desired her closer presence. In 1951, she accepted a fellowship at King's College London to apply X-ray crystallography to biological molecules. The project was linked to Maurice Wilkins, who was investigating DNA fibers. Franklin's move marked the beginning of the most famous, and in many ways, the most contentious period of her career. At King's College London, Franklin was appointed to work on DNA, which was emerging as a molecule of profound biological importance. The nature of DNA's structure remained unknown, and solving it promised to revolutionize biology. Franklin brought to the project her expertise in crystallography and her insistence on experimental rigor. However, the environment at King's was less welcoming than Paris. From the start, she encountered tensions, particularly with Wilkins, whose expectations about collaboration did not align with Franklin's understanding of her independent research role. When Rosalind Franklin arrived at King's College London in early 1951, she was tasked with applying X-ray crystallography to the study of DNA fibers. DNA, or deoxyribonucleic acid, was already suspected to hold the secret of heredity, but its structure remained a mystery. Franklin immediately began designing a more precise experimental approach. She refined methods for hydrating DNA fibers, enabling her to capture clearer diffraction patterns than had ever been obtained. Her meticulous style brought a new level of accuracy to the project. Franklin was soon partnered, at least in theory, with Maurice Wilkins, a biophysicist who had been exploring DNA fibers. However, their collaboration faltered almost immediately. Wilkins assumed Franklin would serve in a supporting role to his work, while Franklin believed she had been recruited to lead her own independent investigations. This misunderstanding sowed tension. Franklin's assertive, no-nonsense personality clashed with Wilkins's more reserved style. Miscommunications compounded, leaving the two scientists working uneasily alongside each other rather than in true partnership. Despite the interpersonal difficulties, Franklin's technical progress was remarkable. She quickly identified that DNA fibers could exist in two distinct forms depending on their hydration level. She labeled these the A and B forms. Each produced a different diffraction pattern, suggesting that DNA molecules had a structural flexibility previously unappreciated. By carefully controlling experimental conditions, Franklin captured exceptionally sharp images of both forms. This discovery proved essential, as the B-form images would eventually provide the clearest window into DNA's true double helical architecture. Among Franklin's most celebrated contributions was the now famous Photograph 51, an X-ray diffraction image of the B-form of DNA taken in 1952. This image displayed a distinct cross-shaped pattern, immediately recognizable to crystallographers as the signature of a helical structure. Franklin, cautious and thorough, did not rush to interpret it. She wanted additional data before proposing a definitive model. Her hesitancy was rooted in scientific rigor, but this caution later contributed to others capitalizing on her results before she could publish them herself. Franklin approached the DNA problem with systematic precision. She methodically analyzed the diffraction patterns, calculated helical parameters, and carefully recorded her observations. Her notebooks reveal her deepening insight into DNA's repeating helical nature. She even estimated the molecule's dimensions with striking accuracy. However, her reluctance to speculate without exhaustive evidence contrasted with the approach of Francis Crick and James Watson at Cambridge, who were simultaneously attempting to solve DNA's structure. Their style relied heavily on building theoretical models rather than exhaustive experimental verification. The environment at King's College was not always conducive to Franklin's work. The laboratory facilities were far from ideal, and the culture was often unwelcoming to women scientists. Franklin faced subtle and overt discrimination, from being excluded from informal gatherings to encountering resistance when asserting authority over her research. Despite these obstacles, she remained determined and professional. She immersed herself in her experiments, producing results of extraordinary clarity. Her persistence amid adversity underscored her resilience and highlighted the broader gender barriers facing women in mid-20th century science. Meanwhile, at the Cavendish Laboratory in Cambridge, James Watson and Francis Crick pursued DNA's structure using model building. They relied heavily on published data and informal reports from other scientists. The competition between King's College and Cambridge was fierce, with both groups racing toward a breakthrough. Franklin, though less inclined toward competition, found herself unwillingly drawn into the contest. Unbeknownst to her, some of her most important findings, including Photograph 51, were shared with Watson and Crick without her knowledge or explicit consent. In early 1953, Wilkins showed Photograph 51 to James Watson, who immediately recognized its significance. The image confirmed his suspicion that DNA was a double helix. Along with a report summarizing Franklin's data, this information provided the missing pieces Watson and Crick needed to finalize their model. They quickly constructed a double helical model of DNA, incorporating Franklin's precise measurements of the helical pitch and the spacing between bases. Their model was elegant, explanatory, and ultimately correct. However, Franklin was not informed about the use of her data. Franklin continued her own analyses, and by the spring of 1953, she had reached conclusions consistent with a helical structure. Her drafts and notebooks reveal that she was on the verge of describing DNA as a double helix with bases oriented inward. Yet, before she could publish, Watson and Crick announced their model in Nature. Franklin's own papers, published in the same issue, provided crucial experimental confirmation. The arrangement made it appear collaborative, though in reality, Franklin had been working independently without knowledge of Cambridge's reliance on her findings. The publication of Watson and Crick's DNA model in April 1953 marked a watershed moment in biology, laying the foundation for modern genetics. Franklin's contribution was vital, but at the time, her role received little public acknowledgement. Watson and Crick were celebrated, while Franklin, though credited in print, remained in the shadows. She accepted the situation with dignity, focusing instead on continuing her research. For Franklin, the pursuit of truth through science was more important than recognition, though later generations would re-evaluate her indispensable role. After the publication of Watson and Crick's DNA model in 1953, Rosalind Franklin accepted a position at Birkbeck College, London. She joined J.D. Bernal's laboratory, which was renowned for structural studies on biological molecules. At Birkbeck, she shifted her focus away from DNA, leaving behind the contentious atmosphere at King's College. Instead, she turned to studying viruses, particularly the tobacco mosaic virus, TMV. This new direction allowed Franklin to apply her crystallographic expertise to an emerging frontier in structural biology. Franklin's transition to virus research was seamless because her crystallographic methods could be adapted to new molecular systems. TMV, a rod-shaped virus that infects plants, was an ideal target. Understanding its structure promised insights not only into plant pathology but also into the principles of viral architecture more generally. Franklin brought her trademark rigor to the project, designing experiments with precise controls and careful documentation. She soon began producing diffraction images of TMV that matched, in clarity and importance, the DNA photographs she had pioneered earlier. At Birkbeck, Franklin thrived in a more supportive and collaborative environment. Bernal valued her independence and provided resources without interference. The atmosphere contrasted sharply with the conflicts at King's College, and Franklin was able to build a cohesive research group of her own. Among her colleagues were Aaron Klug, who later won the Nobel Prize, and Don Casper, who collaborated on virus structures. These younger scientists admired Franklin's intensity, discipline, and commitment to precision. She also became a respected mentor, guiding her students with the same standards she applied to herself. Franklin's work on TMV led to significant breakthroughs. She demonstrated that the virus consisted of a single strand of RNA wound inside a protein sheath in a helical arrangement. This discovery confirmed earlier hypotheses but provided the most detailed evidence yet. She calculated dimensions of the helical coil with extraordinary accuracy, paralleling her success with DNA. Franklin's results not only advanced virology but also supported the growing field of molecular biology. Her careful approach showed how viruses could be studied structurally, bridging chemistry, biology, and medicine. In addition to TMV, Franklin began studying other viruses, including the poliovirus. This research was ambitious and medically relevant, given polio's devastating impact worldwide during the 1950s. Franklin applied crystallography to investigate the virus's symmetry and protein composition. Though this work was still in early stages at the time of her death, it laid a foundation for future discoveries. Her team, continued by Aaron Klug after her passing, built on these beginnings to produce insights that would shape modern virology. Franklin thus helped establish virus research as a central branch of molecular science. The collegial atmosphere at Birkbeck also allowed Franklin to engage more fully with the broader scientific community. She attended conferences, exchanged ideas internationally, and collaborated with physicists, chemists, and biologists. She traveled extensively during these years, giving lectures and presenting her findings at meetings in the United States and Europe. Colleagues recalled her as a clear, forceful speaker who conveyed complex data with precision. These opportunities not only raised her professional profile but also highlighted her versatility. She was no longer defined solely by her DNA research. Despite her professional success, Franklin's personal life remained relatively private. She valued close friendships, particularly with her scientific peers, but she devoted most of her time to research. Some accounts suggest she longed for deeper personal relationships, while others emphasize that she felt most fulfilled by science. She enjoyed hiking, traveling, and engaging in cultural activities, especially during her Paris years, but at Birkbeck, her time was dominated by research responsibilities. Friends described her as warm and witty in private, yet intensely focused when in professional settings. Franklin's achievements at Birkbeck further demonstrated her resilience and adaptability. After the disappointments of the DNA episode, she reinvented herself in a new field, producing work that was equally groundbreaking. Her leadership at Birkbeck challenged stereotypes about women in science, showing that she could not only conduct pioneering research but also direct an influential laboratory. Her contributions during this period helped establish structural virology as a rigorous discipline. Many later scientists, including Nobel laureates, traced their intellectual lineage to Franklin's work in this area. By the mid-1950s, Franklin's career was flourishing. She had published a series of important papers, secured grants for her research, and was widely recognized as an authority in X-ray crystallography. Her collaborations expanded internationally, and she was increasingly in demand as a speaker. Colleagues admired her ability to balance scientific vision with exacting detail. Yet even as her career reached its peak, Franklin's health began to decline. In 1956, she was diagnosed with ovarian cancer, a disease that would tragically end her life within 2 years. Franklin faced her illness with the same courage and determination she brought to her research. Despite undergoing surgeries and chemotherapy, she continued working almost without pause. She published papers, attended conferences, and guided her team at Birkbeck with undiminished intensity. Friends and colleagues were astonished at her resilience. She rarely complained, preferring to focus on her experiments rather than her pain. Even as the disease progressed, she remained deeply engaged with science, pushing forward projects that she knew might outlast her own involvement. Rosalind Franklin's diagnosis of ovarian cancer in 1956 was a devastating blow, yet she confronted it with characteristic determination. Medical treatments of the time were limited, and surgery followed by chemotherapy offered only partial relief. Still, Franklin refused to retreat from her work. She maintained her research schedule, continuing to produce high-quality results. For her, science was not merely a career but a driving force that gave her life meaning, even as illness increasingly burdened her physically and emotionally. Throughout 1956 and 1957, Franklin balanced her medical treatments with intensive scientific output. She published important papers on the tobacco mosaic virus, expanding understanding of its helical symmetry and RNA placement. She also collaborated with Aaron Klug and Don Casper on projects that would later lead to Nobel-winning discoveries. Her colleagues admired her unwavering dedication. Even as she endured physical exhaustion, she refused to lower her standards. She corrected data meticulously, reviewed drafts critically, and insisted on maintaining the same precision that defined her earlier work. During this period, Franklin also strengthened her collaborations with American scientists. She traveled to the United States to lecture and exchange ideas, despite her illness. At Yale and Caltech, she impressed audiences with her clarity and depth of knowledge. These trips reflected her international standing as a crystallographer and virus researcher. American colleagues later recalled her brilliance and determination, noting that she seemed undeterred by personal hardships. Franklin's presence in these circles helped solidify her reputation as a leading figure in structural biology. Franklin's illness, however, progressed relentlessly. She underwent multiple surgeries, including operations to remove tumors, but the cancer recurred. Chemotherapy treatments left her weak, though she rarely revealed her suffering. Instead, she remained optimistic in front of her colleagues, sometimes even making light of her condition. Those close to her described her as courageous and stoic, with an unshakable commitment to her work. She never allowed illness to define her identity. Instead, she chose to be remembered as a scientist who continued working until the end. As Franklin's health declined, her colleagues at Birkbeck grew protective of her. Aaron Klug, in particular, became both a collaborator and a supportive friend. Together, they produced groundbreaking studies on TMV and extended their research to other viruses. Klug later credited Franklin with shaping his scientific approach, emphasizing rigorous experimentation and intellectual honesty. Their partnership highlighted Franklin's generosity as a mentor, even when her time was limited. She invested in younger scientists, ensuring that her influence would endure beyond her own research contributions. In 1957, Franklin began exploring the poliovirus, a project of urgent medical relevance given the ongoing polio epidemics worldwide. Her goal was to determine the virus's structural organization using crystallographic methods. Although she did not live long enough to complete this work, her preliminary studies laid the groundwork for later breakthroughs. After her death, Klug and his team carried the research forward, building on the foundations Franklin had established. In this way, her final projects continued to bear fruit long after her passing. Despite her deteriorating health, Franklin managed to sustain a balance of professional dedication and personal engagement. She remained close to her family, particularly her parents and siblings, who supported her during hospitalizations and treatments. She also maintained friendships with colleagues, sometimes spending weekends in the countryside to regain strength. These moments of respite were cherished, though brief. Franklin's resilience impressed everyone around her. She embodied both intellectual strength and personal courage, qualities that would later form a central part of her legacy as a pioneering scientist. By early 1958, Franklin's condition had worsened significantly. She was frequently hospitalized, but even from her hospital bed, she continued reviewing papers and discussing research. Colleagues brought manuscripts for her approval, and she insisted on staying informed about ongoing projects. This extraordinary persistence reflected her lifelong commitment to science. She understood that her illness was terminal, yet she preferred to concentrate on the work still within her control. Her determination became a testament to the depth of her scientific passion. Rosalind Franklin died on 16 April 1958 at the age of 37. Her death came only 5 years after the publication of Watson and Crick's DNA model. The scientific world lost one of its most brilliant experimentalists at the height of her intellectual powers. Her colleagues mourned not only her passing but also the unfinished work she left behind. At her funeral, friends and family remembered her seriousness, brilliance, and humanity. Though her life was cut short, her influence on molecular biology was already profound. After her death, Franklin's colleagues ensured that her unfinished projects were carried forward. Aaron Klug, in particular, inherited her virus research program and later received the Nobel Prize in Chemistry in 1982 for his work on virus structures. Klug always emphasized Franklin's foundational role in this research, acknowledging that his achievements were built upon the base she had established. In this sense, Franklin's legacy extended beyond her DNA work, influencing multiple scientific fields. She had demonstrated that meticulous crystallography could unlock the secrets of life. Rosalind Franklin's death in 1958 meant that she never witnessed the full impact of her contributions to molecular biology. Only 5 years later, in 1962, the Nobel Prize in Physiology or Medicine was awarded to James Watson, Francis Crick, and Maurice Wilkins for their discovery of DNA's structure. Franklin's absence from this honor immediately raised questions among those who knew her importance. Nobel rules prohibit posthumous awards, but many believed that had she lived, she would have shared in the recognition. The Nobel Prize announcement cemented Watson, Crick, and Wilkins as central figures in biology's revolution, but Franklin's role remained overshadowed. Public accounts of DNA's discovery often minimized or ignored her contributions. Watson's 1968 memoir The Double Helix further shaped perceptions, portraying Franklin in unflattering and dismissive terms. He referred to her as Rosie, a nickname she never used, and depicted her as argumentative rather than brilliant. The book's popularity reinforced stereotypes that obscured Franklin's true role in solving DNA's structure. Many contemporaries and later historians criticized Watson's account for its inaccuracies and gendered bias. Colleagues from King's College and Birkbeck defended Franklin's professionalism, emphasizing her meticulous data collection and intellectual contributions. They argued that her caution and insistence on rigorous evidence were not weaknesses but strengths, ensuring that the DNA model was built on solid experimental ground. As feminist scholarship grew during the 1970s and 1980s, Franklin became a symbol of women's under-recognized labor in science, prompting widespread re-evaluation of her career. Anne Sayer's 1975 biography Rosalind Franklin and DNA was pivotal in reshaping Franklin's public image. Sayer, a personal friend, countered Watson's dismissive portrayal and emphasized Franklin's integrity, brilliance, and essential role in the DNA story. The book highlighted how systemic sexism influenced both her treatment at King's and the subsequent neglect of her contributions. Sayer's work galvanized public interest, presenting Franklin not merely as a supporting figure but as a central protagonist in one of science's greatest discoveries. Subsequent historical studies further established Franklin's contributions. Her notebooks and reports, preserved at King's College, provided undeniable evidence that she had recognized DNA's helical structure and measured its key dimensions before Watson and Crick's announcement. Scholars emphasized that her data were not incidental but foundational. Without photograph 51 and Franklin's precise calculations, Watson and Crick's model would have lacked confirmation. The re-evaluation reframed the DNA discovery as a collective achievement, not simply the triumph of two theorists at Cambridge. The debate over Franklin's recognition also revealed broader issues about collaboration, competition, and credit in science. At King's College, ambiguous administrative arrangements had left Franklin and Wilkins unclear about their respective responsibilities. This lack of clarity fostered tension and allowed misunderstandings to flourish. Meanwhile, scientific culture at the time often minimized women's authority, further marginalizing Franklin. Later generations saw in her story a cautionary tale about how institutional structures and cultural biases can distort the historical record of discovery. In the decades following her death, Franklin's reputation steadily rose. Universities, research institutions, and scientific societies began honoring her with lectureships, buildings, and awards bearing her name. The Rosalind Franklin Institute, established in Oxfordshire in the 21st century, symbolizes the growing acknowledgement of her role. Such honors underscore that her legacy extends beyond DNA to crystallography, coal research, and virology. They also reflect the scientific community's attempt to rectify past neglect and ensure that her story inspires future generations of researchers. Franklin's case also became emblematic of the challenges faced by women in science. Her experiences highlighted how even the most talented women were often marginalized, misrepresented, or denied full credit. Feminist historians used her life as a lens to examine systemic inequities in academia, from limited career opportunities to cultural biases. In this way, Franklin's legacy transcended biology, influencing broader conversations about gender equality in scientific institutions. She became both a role model for aspiring scientists and a symbol of structural injustice. Interestingly, Franklin herself may not have sought the kind of recognition that later advocates demanded on her behalf. Those who knew her recalled that she valued scientific truth more than fame. She disliked speculation and resisted premature conclusions, preferring meticulous data over sweeping theories. This temperament meant she was less likely to engage in the competitive, public race for recognition. Nevertheless, her contemporaries acknowledged her brilliance privately, and her colleagues at Birkbeck always described her as the intellectual leader of their group. By the late 20th century, Franklin's role in the DNA story had become widely accepted in scientific histories. Textbooks began to acknowledge her contributions, and popular media increasingly portrayed her as an essential figure. Plays, documentaries, and novels brought her story to wider audiences. Works such as Anna Ziegler's play Photograph 51 dramatized the ethical questions surrounding her exclusion from recognition. Through these cultural representations, Franklin became not only a scientific icon but also a symbol in broader narratives about fairness, justice, and gender equality. Rosalind Franklin's approach to science reflected a philosophy rooted in precision, patience, and skepticism of untested assumptions. She believed that nature's secrets revealed themselves only through rigorous experimentation. This made her cautious about drawing conclusions prematurely, but also ensured that her findings were consistently reliable. Franklin's insistence on evidence-based research occasionally frustrated colleagues eager for bold theoretical leaps, yet her careful methodology often prevented errors. Her scientific philosophy ultimately ensured that her contributions endured, providing solid foundations upon which others could build. Her personality was complex, shaped by both her intellectual intensity and her independent spirit. Friends described her as serious, disciplined, and sometimes intimidating in professional contexts. Yet in personal settings, Franklin displayed warmth, humor, and loyalty. She loved hiking, traveling, and immersing herself in art and literature. She also valued close friendships, especially with colleagues who shared her dedication to science. This duality, private warmth coupled with professional intensity, explains why some contemporaries misunderstood her, interpreting her determination as aloofness rather than commitment to excellence. Franklin's seriousness in the laboratory derived from her deep respect for scientific work. She believed experiments should be conducted with integrity and without shortcuts. Her notebooks, preserved in archives, reveal meticulous entries, precise calculations, and detailed observations. She held herself and her colleagues to high standards, which could sometimes lead to tensions, but her commitment inspired younger scientists. Franklin also had a moral seriousness, shaped by her Jewish heritage and her family's emphasis on service. She felt a responsibility to contribute meaningfully to human knowledge. Although often portrayed as a solitary figure, Franklin thrived in collaborative environments when mutual respect was present. Her years in Paris illustrated her ability to integrate socially and professionally. She enjoyed engaging with French colleagues, attending cultural events, and discussing ideas over meals. At Birkbeck, she fostered a supportive group dynamic, mentoring Aaron Klug and others with patience and generosity. These experiences showed that Franklin was not inherently difficult but rather thrived when treated as an equal. Misunderstandings at King's reflected institutional failures more than personal shortcomings. Franklin's broader impact lies in how her story reshaped cultural conversations about science. She became an emblem of the invisible labor behind great discoveries, reminding historians that breakthroughs are rarely the work of a single genius. Her contributions demonstrated the indispensable role of experimentalists in validating theories. Moreover, her life story drew attention to the systemic challenges women faced in mid-20th century academia. In this way, Franklin's legacy reached beyond molecular biology, influencing how society understands the practice of science and the distribution of credit. Her influence extended to education, where her example inspired curricula highlighting women in science. By the late 20th century, Rosalind Franklin was included alongside Marie Curie and Barbara McClintock as role models for aspiring scientists. Teachers emphasized her perseverance, her precision, and her courage in navigating male-dominated institutions. She became a powerful counter-narrative to stereotypes that questioned women's capacity for rigorous scientific work. In this sense, Franklin's legacy was not confined to laboratories. It reached classrooms, inspiring generations of students to pursue scientific careers. Franklin's legacy also influenced debates about ethics in science. The unauthorized sharing of her data with Watson and Crick raised enduring questions about collaboration, competition, and credit. Historians and ethicists used her case to illustrate the importance of consent and transparency in research. These debates informed later policies on authorship, data sharing, and recognition in collaborative projects. Thus, Franklin indirectly contributed to shaping modern scientific norms. Her story serves as a reminder that discoveries involve not only intellect but also ethical responsibilities toward colleagues. Her influence on the philosophy of science was equally significant. Franklin's cautious empiricism contrasted with the more speculative style of her contemporaries. This tension highlighted the value of diverse approaches within scientific progress. Theorists like Watson and Crick needed experimentalists like Franklin to ground their models. The interplay of these methods demonstrated that scientific discovery thrives on both imagination and rigor. Franklin's life thus exemplifies the necessity of balance in research. Visionary ideas require careful testing, and precise data often inspire transformative theories. Franklin's personality was also shaped by resilience. Throughout her career, she confronted sexism, professional rivalries, and eventually terminal illness. Yet she maintained focus, producing world-class research under conditions that might have defeated others. This resilience became part of her cultural image. Biographies, plays, and documentaries often highlight her stoicism in the face of adversity. She emerged as a symbol of perseverance, showing how individuals can transcend personal and institutional obstacles to leave lasting marks on human knowledge. Her resilience continues to inspire scientists today. Her reputation underwent significant transformation after her death. Initially overlooked, she was later celebrated as an icon of both science and feminism. This dual recognition reflects the multifaceted nature of her legacy. As a scientist, she provided critical data on DNA and viruses. As a cultural figure, she highlighted systemic inequities and inspired reforms. The evolution of her reputation illustrates how history is continually rewritten as new evidence emerges and societal values shift. Franklin's story thus remains dynamic, resonating across generations. After Rosalind Franklin's untimely death in 1958, her scientific contributions remained undervalued for decades. Yet, gradually, institutions across the world began recognizing her achievements. Universities named laboratories, research centers, and fellowships in her honor. These gestures acknowledged both her pioneering work and the injustice of her overlooked role in the discovery of DNA. Each commemoration served as a corrective act, reminding future generations that history had once failed to honor a scientist whose work fundamentally reshaped molecular biology and medicine. One of the most significant memorials is the Rosalind Franklin University of Medicine and Science in Chicago, named in 2004. This institution emphasizes health sciences and biomedical research, reflecting Franklin's lifelong dedication to applying science for human benefit. The university's mission honors her ethos of precision, integrity, and collaboration. By carrying her name, the institution ensures that thousands of students encounter Franklin's legacy not merely as history but as an ongoing source of inspiration for careers in science and medicine. In Britain, her legacy is most visibly celebrated at Birkbeck College, where she conducted groundbreaking virus research in her final years. A building on campus bears her name, symbolizing the respect of an institution where she thrived professionally. The naming acknowledges her impact on structural biology and her role as a mentor to Aaron Klug, who later received the Nobel Prize. Through this recognition, Birkbeck publicly affirms Franklin's enduring influence on its scientific community and the broader field of crystallography. Her memory has also been enshrined through prestigious fellowships and scholarships supporting young scientists, particularly women. These programs encourage research in the natural sciences, echoing Franklin's determination to expand knowledge. Such initiatives both commemorate her and extend her legacy by enabling future generations to continue the type of rigorous, impactful research she championed. By linking her name to educational opportunities, these fellowships ensure Franklin's story inspires practical change, addressing gender imbalances she herself struggled against during her career. Franklin's recognition extends to celestial honors. In 1997, a crater on the Moon was named Franklin in her honor, placing her legacy among the stars. This tribute acknowledged her contributions not only to earthly science but to humanity's broader quest for knowledge of the universe. Similarly, asteroid 9241 Rosfrank was named after her, embedding her legacy within astronomical maps. These cosmic memorials symbolize the universality of her contributions and affirm her place among the great scientific pioneers of history. Beyond physical landmarks, Franklin's legacy has been perpetuated through cultural commemorations. Plays, novels, and documentaries have dramatized her life, ensuring her story reaches audiences far beyond academic circles. Works such as Photograph 51 by Anna Ziegler spotlighted her struggle for recognition and gave voice to her perspective. These cultural portrayals reshaped public understanding, humanizing Franklin as both a brilliant scientist and a woman navigating systemic barriers. Such narratives reinforced her place in collective memory, transforming her from a footnote into a cultural icon. Government institutions also embraced her legacy. In 2020, the UK government announced that the planned rover for the European Space Agency's Mars mission would be named the Rosalind Franklin rover. This gesture placed her name at the forefront of planetary exploration, connecting her pioneering DNA research with humanity's next frontier, the search for life beyond Earth. The rover's name symbolized continuity between her structural biology work and modern astrobiology, underscoring how Franklin's spirit of inquiry continues to guide scientific exploration. Her legacy has been celebrated in stamps, coins, and public exhibitions, further embedding her memory in national and international consciousness. The Royal Mail issued a stamp featuring her in 2020, part of a series honoring scientific greats. Exhibitions in museums across Europe and America have dedicated space to Franklin's contributions, ensuring visitors understand her essential role in unlocking DNA's mysteries. These public recognitions counteract decades of historical neglect, affirming her rightful place alongside other scientific luminaries like Darwin, Newton, and Curie. Rosalind Franklin's name also appears in countless academic articles, textbooks, and conferences, signifying her permanent place in scientific discourse. Students of biology and medicine frequently encounter her contributions early in their studies, learning about X-ray diffraction patterns and the significance of photograph 51. By making her work central to the scientific curriculum, educators ensure her influence extends far beyond her short lifetime. Each citation and classroom discussion reinforces the idea that her achievements are foundational, not supplementary, to molecular biology. The ongoing recognition of Franklin illustrates how scientific history is constantly being revised. What was once neglected is now celebrated, reflecting society's growing awareness of gender inequities in science. Her memorials remind us that recognition is not static but can evolve as new generations reassess the past. In this way, Franklin's posthumous honors are not merely tributes to her but also cultural acts of justice, correcting historical oversight and ensuring that her contributions remain visible in the narrative of human discovery. Rosalind Franklin's story became a touchstone for discussions about women in science. Her experiences at King's College, where she faced professional marginalization and gender-based obstacles, highlighted systemic inequities that persisted in academia. Feminist historians emphasized her brilliance, contrasting it with the lack of recognition she received during her lifetime. Franklin became a symbol of resilience and capability, demonstrating that women could contribute at the highest levels of scientific achievement despite institutional barriers that sought to limit their opportunities. Her legacy influenced policies promoting gender equality in scientific research. Universities and funding agencies began establishing programs aimed at increasing female participation in STEM. Franklin's story was often cited as evidence that talented women had historically been overlooked and that proactive measures were necessary to prevent continued exclusion. By embodying both extraordinary ability and professional challenges, she became an exemplar for why equitable representation in science matters, inspiring structural reforms in hiring, mentoring, and research funding for women. Franklin's life also inspired individual scientists, especially young women entering the field. Biographies, plays, and documentaries highlighted her diligence, precision, and intellectual independence. For many, Franklin became a role model demonstrating that women could lead groundbreaking research. These narratives encouraged mentorship networks, scholarships, and academic societies focused on supporting women in chemistry, biology, and physics. Franklin's perseverance and scientific integrity showed that success in research was attainable, even in environments historically dominated by men. Her experience also contributed to broader debates about authorship and recognition in collaborative science. Franklin's exclusion from immediate acknowledgement in the DNA discovery exposed flaws in how credit was allocated. These discussions led to policy changes in research ethics, emphasizing transparency, proper citation, and acknowledgement of all contributors. By studying Franklin's life, institutions recognized the need for mechanisms to protect junior scientists and those in underrepresented groups from being marginalized, ensuring that scientific achievements were fairly documented and celebrated. Cultural representations of Franklin reinforced her feminist legacy. Playwrights, novelists, and filmmakers emphasized her struggle for acknowledgement in a male-dominated field. Through these portrayals, Franklin's narrative became a rallying point for gender equality in STEM, showing how societal norms could impede talent. By highlighting both her brilliance and the obstacles she faced, these works fostered awareness and advocacy. Franklin thus became both a scientific and cultural symbol, inspiring campaigns and educational initiatives aimed at increasing women's participation in research globally. Her story also intersects with discussions about mentorship in science. Franklin's guidance of younger scientists at Birkbeck, particularly Aaron Klug, demonstrated her willingness to share knowledge and foster talent. Feminist scholars emphasized how her mentorship contrasted with the competitive exclusion she herself experienced. By mentoring effectively, Franklin ensured her intellectual legacy continued, demonstrating that support and collaboration were essential for equitable scientific progress. This duality, mentorship alongside personal struggle, made her influence enduring and multifaceted. Rosalind Franklin's impact on STEM culture is evident in ongoing initiatives celebrating women in science. Awards, fellowships, and lecture series named after her aim to inspire young scientists, especially girls, to pursue challenging research fields. Her example underscores the importance of resilience, rigor, and intellectual courage. Institutions use her story to emphasize that barriers can be overcome, and that historically marginalized voices are essential to innovation. Franklin's life thus functions both as a cautionary tale and as a source of inspiration for systemic change. Her name also symbolizes the integration of feminist thought with scientific practice. Scholars use her life to explore how gender biases shape knowledge production and recognition. Franklin's experience provides a lens to study the sociocultural context of scientific discovery, highlighting intersections of gender, authority, and merit. By examining her career, historians and sociologists gain insight into the structural challenges that have historically constrained women, and the ways exceptional talent can both confront and transcend these obstacles. Franklin's story continues to influence public understanding of women in science. Museum exhibitions, educational curricula, and media productions highlight her contributions to DNA research and virology. By situating her achievements alongside her struggles, these representations encourage reflection on systemic inequities. Franklin's narrative also sparks discussion about how scientific institutions can foster inclusive cultures. In this way, she remains a living symbol. Her life and work are not merely historical facts but instruments of cultural and educational change, inspiring both scientific inquiry and social progress. Her feminist legacy extends internationally. Scholars and organizations around the world cite Franklin as a model for promoting diversity and inclusion in STEM. Conferences on women in science frequently feature her as a case study of brilliance constrained by gender norms. By highlighting her accomplishments alongside the obstacles she faced, these discussions underscore the need for ongoing reform. Franklin's story resonates across disciplines and cultures, illustrating that progress in science is inseparable from progress in equity and social justice. Rosalind Franklin's scientific contributions continue to influence research today. Her work on DNA's B form remains a foundational reference in molecular biology, while her virus research laid the groundwork for structural virology. Modern X-ray crystallography and cryo-electron microscopy often build on principles she refined decades ago. Franklin's approach, combining meticulous experimentation with rigorous analysis, remains a standard for laboratory practice, demonstrating that the methods she developed are as important as the discoveries themselves. Her pioneering virus studies contributed to the understanding of viral assembly and RNA organization. Researchers today still reference her TMV findings when investigating viral structures, including those of pathogens affecting humans. Franklin's precision in measuring helical structures and her innovative techniques influenced the development of modern antiviral strategies and vaccine research. Her insights into virus morphology paved the way for both theoretical models and practical applications, showing how foundational science can have broad, lasting impacts on medicine and public health. Franklin's work continues to inspire methodological rigor. In contemporary molecular biology, her insistence on precise measurements, detailed documentation, and replication of results serves as a pedagogical model. Students and young researchers are encouraged to emulate her approach: thorough preparation, critical analysis, and cautious interpretation. By emphasizing methodology as much as results, Franklin left a legacy that transcends her discoveries, shaping the way science is conducted across disciplines and ensuring that future generations inherit her standard of excellence. Modern DNA research also owes much to Franklin's findings. Her measurement of the helical pitch and base spacing directly informed the double helix model, which underpins genetics, genomics, and biotechnology. Advances such as CRISPR gene editing, personalized medicine, and molecular diagnostics trace conceptual lineage back to her contributions. While Watson and Crick popularized the double helix, Franklin's experimental rigor ensured that their model had empirical credibility. Without her data, the foundation of modern molecular biology would have been significantly weaker.